Cambridge Computer Science, Chapter 1, Data Representation, Part 2. We start here studying about how you can represent positive and negative numbers. Previously, we were only studying how to do positive numbers only, positive integer numbers. Now we would like to have space for negative numbers. The point is, inside the computer, we only have ones and zeros. So you can never have that dash to represent a negative number. There should be a way of encoding positive and negative numbers using only ones and zeros. Okay? So we will study now a very successful and scientific way of representing positive and negative number, and this is called the 2's complement. There is some science behind, but it is really successful because when you apply the 2's complement to a number, it changes to its negative equivalent. We can just learn and practice how this is working, and you will find it very, very useful. Okay? So we start here with 2's complement to represent positive and negative numbers. When the 2's complement, we use the 2's complement to represent positive and negative integers. Numbers with fractions will not be studied here at all. Will be studied in the A2. Not now. Column headings in 2's complement for 8 bits will be as follows. So if you have 8 bits, column headings will be as follows. Starting from the right, it will be 1, 2, 4, 8, 16, 32, 64. The new thing, the column on the far left, instead of being 128, will be negative 120. This is for 8 bits. If you have 12 bits, column headings will be 1, 2, 4, 8, 16, 32, 64, 1 to 8, and so on, 256, 512, 1024. And the column heading on the far left will be negative 2048 instead of being 2048. So the rule is, if you have 8 bits or if you have 12 bits, the column on the far left will have a negative value. The negative value that should have been positive. So it should have been 128. We would make it negative 120. Okay? This is how column headings are represented in the form of 2's complement. Okay, let us try to practice about converting numbers in 2's complement into denary. Okay, let us look at this example. This example is really simple. So you have a number that is 0, 1, 1, 0, 0, 1, 0, 1. Okay, I always read a number from the left. However, I put weights from the right. Okay, so this number has a 0 on the far left. So it will not have any negative component. It will just be positive because the negative 128 is multiplied by 0. So it is gone. I can give you an advice. If you have a number in 2's complement, and you'd like to know, will that be a positive or negative? At the end, look at the far left digit. If it is a 0, then it will be a positive number. If it is a 1, it's going to be a negative number, and I will show you how. Okay? So if you would like to convert that number into denary, you just add 64 plus 32 plus 4 plus 1, and this is just 101 because there is nothing negative, there is nothing new. Okay, if we look at the other example, we have 1, 1, 0, 0, 1, 0, 1, 1. Okay, you have a look at the far left, there is a 1 here that negative 128 will eventually outweigh all other weights, will outweigh the summation of all other weights. Okay, okay, just now it is not only adding, it is adding and subtracting, and you have to practice this with your hand because calculators are not allowed. Okay, so it is negative 128 plus 64 plus 8 plus 2 plus 1, that is negative 53. I would like you to do this by hand. I would like you, because for example, how can you do it? Please do it by hand. How can you do it? You add the 64 plus 8 plus 2 plus 1, and then you think that, okay, the answer will be negative. So you do 128 minus that summation, and the result will be negative. Just, I will give you some times to try it by hand. Okay, now you know how to subtract them. Okay, let us go through it bit by bit. I have a way of converting a number, a binary number, into its equivalent to 2's complement number. And this is exactly negating a number. So changing its value to something negative. I will show you a number, an example, and I will apply my method. This is called FAST method. I will show you the method to find the equivalent 2's complement for a number. And hopefully we will try to evaluate numbers, and hopefully the number after conversion will be exactly the negative value of the number before conversion. Let us have a look at my method first. It's not my method, it's the method I teach. Okay, let us have look at that method and then try and play with numbers until we are really convinced that is really working. Okay? Okay, if you need to convert a binary number to its 2's complement, we do the following. Starting at the least significant bit, which means on the right. Starting on the right. Okay? And moving left. So you start on the right and move left. Any zeros up to the first one, copy any zeros up to the first one, which is also copied as it is. This needs clarification. I will show you an example. Okay, any remaining bits are then changed from 0 to 1 or from 1 to 0. Let me show you an example, because when you see it once, you will know it easily, inshallah. Okay, let us have this value. It is 0, 1, 0, 1, 1, 1, 1, 1, 1, 0, 0. This is 12 bits number, and it is in the 2's complement form. I would like to convert it to negative. Okay, let us start applying this rule. Starting from the right, let me try to show things together. Starting from the right, if you find zeros, copies them the way you are to the new number. Okay, so you start from the right and copy all the zeros you find the way they are until you find the first one, and then copy it also the way it is. Afterwards, you flip. Any zero, you copy it as 1. Any 1, you copy it as 0. Okay, so starting from here, you have a 0, and 1. This will be here the way they are. After finding that first one, everything is flipped. 1 becomes 0, 1 becomes 0, 1, 1, 1, all zeros. Okay, everything is flipped. Okay, okay. Let us now try to prove that this is really the negative of the number. So I am giving you a task. Actually, everything is on screen, but please redo the calculations yourself. This is the number before converting. This is, so it is, this is the number before converting it to negative. Please calculate the denary equivalent of that. Also calculate the denary equivalent of that. If they are just the negative of each other, then you will be convinced that this method is really working. So please, you yourself, you add 1024 plus 256 plus 128 plus 64 plus 32 plus 16 plus 4 plus 8 as it is shown here, and get me the answer. The answer is in front of you, but please work it yourself. Okay, the number after conversion will be negative 2048 plus 512 plus 4. Okay, and please work them both. If the first evaluates to 1532 and the second one evaluates to negative 1532, then you have a confidence. You will have some confidence in that this method is real. Okay, take your time. Okay, they match. So the first one evaluates to positive 1532. The second one, after applying my fast method of finding the two's complement, evaluates into negative 1538 in denary. So this is really the negative equivalent of that number. Okay, let us go and look how they appear in questions. Okay, so how they ask you about that in the exam. Okay, so they ask you to use the two's complement to represent the denary number negative 54. Okay, in 8 bits. So my plan will be as follows. First, I convert the positive 54 into denary. And then I apply the method I have just told. That is, starting from the right, any zeros copied the way they are until you find the first one, which is also copied the way it is, and then afterwards flip. And if you apply that method to the binary representation of positive 54, you will exactly get the representation of negative 54. Okay, so please go ahead. The exam is specifying for you that you will be using 8-bit register. The exam must specify, must say, because when you have 8 bits, you have negative 128. If you have 12 bits, you have something else. Okay, so we are using 8 bits. Okay, so put the weights, convert the 54 into positive 54 into binary, and compute the two's complement and compare your answer with what's in my book. So the binary equivalent of positive 54 will be like that. You cannot put here 1, you cannot put here 1 because 64 is bigger than 54. You put here 1 and subtract. And then here 1. I'm not putting details anymore because you're supposed to be doing that very fast and very accurate right now. So this is the representation, the binary representation of positive 54. We apply the fast method of converting into the equivalent two's complement. Is that starting from the right, any zeros are copied the way they are until you get the first one, which is also copied the way it is. And afterwards, you flip. Okay? So 0 goes as 0, 1 goes as 0, and the rest is flipped. 1 goes as 0, 0 goes as 1. And then you should notice that you will be having a 1 at the far left because this is the column heading with a negative value. This is the negative 128. So now at least you are convinced that this is a negative number. If you have some free time, you could convert that back into denary, it will be exactly -50. Okay, let us go to another example, and these examples are copied from the exams. Okay, do the same story here with -77. Just please go and do it again. Do the same thing with -77. Get the binary equivalent of +77 and apply the conversion method to represent it as -77. So the binary representation of 77 is 0, 1, 0, 0, 1, 1, 0, 1. And applying the method, starting from the right, any zeros, there are no zeros, okay? Then you get the first one, which is copied the way it is, and then you flip. So this is the representation of -77. Okay, do again the -93. I think after all this, okay, now do the -93. Okay, so now you are doing it faster and better. So +93 will be represented like this: 0, 1, 0, 1, 1, 1, 0, 1. Applying the method, starting from the right, you have no zeros. When the number, I would like you to be familiar with numbers. When the number is odd, you will be starting with a 1. When the number is odd, you will be starting with a 1 on the left. Okay, so there are no zeros to copy. You just copy the first one and start flipping. Okay, you may like, for example, in your free time, you compute the binary equivalent, the denary equivalent of that number. Hopefully, it will be exactly -90. Okay, let's move on. Let us move on and give some other examples to clarify more about 2's complement. What do you think would be the range of integer values that is possible to represent in 2's complement integers using a single byte that is 8 bits? When you have 8 bits, the smallest value, which means the most negative value, how can you achieve that? You put a 1 here and fill all these with zeros. This is how you get the smallest value or the biggest negative value. Okay, because this is the only negative component. So the smallest value that can be represented in 8 bits 2's complement is -120. What about how getting the biggest positive value? Put that 0 and fill all others with 1. If you add them, they will be 127. And if you like, for example, because we will be now it is like the maximum value that can be stored in 7 bits. Twice this 64. Twice this is 128. Minus 1 is 120. You may get a question that is asking you to do the same with 12 bits 2's complement. On the far left, you will be having -2040. Okay? Okay, let's move on and study other ideas. Measurement of the size of computer. You know now that the bit is the smallest unit. Okay? That could be either a 0 or a 1. You also know that a byte is 8 bits. There is also something called nibble that is 4 bits. Okay? Then we come to kilo, mega, giga. Okay? Because you have been using that with measurement of, for example, memory or storage size. So let us make it very precise. When the exam is talking to you about kilo, a kilo is 1,000. However, if the exam is giving you kibi, a kibi is 1024. Why? Because they call this denary denomination and they call this binary denominations that are powers of 2. We love in computer science that anything is on the scale of powers of 2. So a kilo, a conventional kilo, a kilogram is 1,000 grams. If the exam is telling you about kilo, then it is 1,000. Kilobyte is 1,000 byte. If the exam is giving you about kibi byte is 1024. Why? Because it is 2 to the power of 10. Mega is 1,000 by 1,000. Bibi is 1,024 multiplied by 1,024. Scientifically, this is 2 to the power of 20. So if you have kilo, mega, giga, tera, peta, everything is 1,000, the previous. If you have kibi, bibi, gibi, tibi, pibi, and maybe also exhibi, I have seen that in an exam. Everything is 1,024, the one before. Or you can say kibi is 2 to the power of 10. Bibi is 2 to the power of 20. Gibi is 2 to the power of 30, to the power of 40, 50, 60. Okay? Definitely, you will never memorize these values. You need to memorize that Kibi is 1,024. Also, Bibi is 1,024 multiplied by 1,024. If you can memorize this, okay, I don't mind. But actually, it is too much. This is too much. Just know that a kilo is 1,000 and a kibi is 1,024. And let us practice this. Let us practice this. Because they are asking you about various conversion methods. Okay, so 8 bits is 1 byte. 800 bits is 1 kilo, because a kilo is 1,000. Okay, 1,000 kilobytes is 1 mega, because this is on the denary scale. 1,024 maybe is 1 GB. 8,192 bits. So if it is 1,024 multiplied by 8, it will be that value. 1,024 multiplied by 8. And this goes to 1 kilobyte. Okay? So see, they question you about what is kilo and what is kibi. Okay? Also, those couple of questions were in the exam. Let us just read them. Let us just read them. Data storage is measured using binary denomination. Binary denomination, which means here powers of 2. Okay? So 8 bytes is 16 nibbles. Why? Because a byte is 2 nibbles. A nibble is 4-bit and a byte is 8 bits. So you at the exam time, you had to fill those values. Okay, 512 kibi is half mibi. Okay, 4 gibi is 4,098 mibi. Why? Because 1 gibi is 1,024 mibi. Multiplied by 4, 1,024 multiplied by 4, this is 4,096. 1 exhibi is 1,024 PB. Okay? Okay. Another, that was on an exam. That was on another exam. 1 TB byte is 1,024 gigabyte. 1 terabyte is 1,000 gigabyte. So I think you need to remember what is written here in those two tables to be able to achieve these values. Okay? In the next session, we will study about hexadecimal.